Hello everyone. In this video we introduce our work Ope-Sr. Currently image super-resolution methods for arbitrary scale are often tackled using the implicit neural representation, INR, which relies on a position encoding scheme to improve representation ability. In the paper, we firstly propose orthogonal position encoding, OPE, an extension of position encoding, for continuous image representation. Secondly, we further designed Ope-Scale module to replace INR-based upsampling module for arbitrary-scale image super-resolution. Although our Ope-Scale module takes 2D coordinates and latent codes as inputs, just like INR, it does not require any training parameters, hence it is computationally efficient and consumes less memory, and achieves comparable results with state-of-the-art method. Existing methods for arbitrary-scale SR typically use a post-upsampling framework. In this approach, low-resolution images first pass through a deep CNN network, encoder, without improving the resolution, and then pass through an INR-based upsampling module, decoder, with a specified target resolution to reconstruct high-resolution, HR, images. The decoder, typically a coordinate-based MLP, establishes a mapping from a pre-assigned grid partitioning to target image pixels based on feature map, the output of encoder, and achieves arbitrary scale via the density property of the grid in Cartesian coordinate system. In the process, sinusoidal positional encoding is introduced to enable the network to learn high-frequency details. In the process, MLP plays a role of universal function approximator. Therefore, it is reasonable to assume that such process could be solved by an analytical solution. In this paper, we re-examine position encoding from the perspective of orthogonal basis and propose orthogonal position encoding, OPE, for continuous image representation. The linear combination of 1D latent code and OPE can directly reconstruct continuous image patch without using MLP. This representation method only requires one position encoding and one matrix multiplication operation when rendering target image pixels. Hence we achieve high computing efficiency and consume less memory after we further propose Ope-Scale module based on OPE representation. The formulation of orthogonal position encoding, OPE, is as follows. Compared to commonly used position encoding formulation, OPE includes a constant term and takes the product of each coordinate embedding as a new term. When we take x, y of OPE as variates, every element of OPE is a basic sinusoidal bivariate function. They are orthonormal basis under our given inner product operation in function space. Hence their linear combination with different weights, or so-called 1D latent code, can directly represent a continuous bivariate function. In OPE representation, a continuous image patch with any resolution can be seen as the discrete sampling result of a bivariate function, which can be decomposed as the linear combination of a 1D latent code and OPE. OPE is the same for every situation. So we could say the 1D latent code directly makes up the continuous image patch without any redundant operations or learnable parameters like MLP. In the paper, we propose OPE from the perspective of functional analysis for the brevity of theory. Someone may be curious about the relationship of OPE and 2D Fourier transform. In fact, the OPE can be seen as the real form version of 2D Fourier basis. Please see the supplementary material for details. Next, I'd like to introduce Ope-Scale module. This is the pipeline of Ope-Sr framework. Like the post-upsampling framework, the low-resolution image first passes through an encoder, the only trainable part, to get feature map. The Ope-Scale module aims to establish a mapping relationship of pre-assigned grid partitioning coordinates and feature map and target image pixels. As mentioned before, a 1D latent code directly makes up the continuous image patch, so we extract them from the feature map over channel dimension. After confirming the latent codes, we calculate relative coordinates of target pixels to the corresponding latent code, and embedding them with OPE. Finally, We get all of the pixels of target image after linear combination operation. Notice the image as RGB channels, so the Ope and linear combination are calculated on every channel respectively. Till now, there are still some little questions, such as how to solve the discontinuity issue at the intersection of adjacent image patches or how to choose a proper frequency of Ope. We recommend the interested readers to read the original paper and supplementary materials for details. Despite our upsampling model is concise and parameter-free, we achieve comparable results with state-of-the-art method. For qualitative results, there was no significant difference. For quantitative results, we narrow the gap between state-of-the-art method and ours in most results less than 0.1 decibels. Compared to other upsampling modules, our Ope upscale module has no parameters, hence it saves memory of intermediate data, for example gradients, hidden layer outputs, and this advantage is fully reflected in training mode of PyTorch. Since it only requires one position encoding and one matrix multiplication operation when rendering target image pixels, we also achieve high computing efficiency. Judged by the time complexity measured by the number of operations, we save 2 orders of magnitude. In image super resolution, Ope has demonstrated its representation potential and established interesting relationship between position encoding and 2D Fourier transform. Further, we believe Ope could be generalized to more research fields to simplify MLP for high-efficient implicit neural representation. We leave more applications of Ope as future works. Thanks for watching.